Okay. So when should I stop? Please remind me. Okay, I should definitely stop early because the last talk everybody need to catch up. Okay. So so first of all, I'm the last speaker, so I definitely should say let's thank the organizer Yvonne Sumio for organizing the wonderful. Okay, so today I will wrap up what is we're trying to do. I will really tell you what is the discrete uniformization problem is. Okay, so the question that we are headed for really is when are two PL surfaces, polyhedral surfaces, at the moment it's any connected surface with a discrete set D marked, and I have two such surfaces. When are these two discrete conformal? So really, it's really a question of how to define this notion of discrete conformal subject to three conditions. The first is computable. So I really want this to be recognizable by a computer. And second of all, I need to have a version of a discrete uniformization theorem. And the third is convergent. So I don't have time to tell you about this, but we do have the correct notion. It lies in the Delaunay condition, which I alluded in the last lecture, which I like to recall, because there are really hyperbolic geometric interpretation of it is the convexity, and then by the end, the discrete uniformization problem is really related to what Gomi mentioned it just an hour ago on the Weyl problem. Okay, so the convexity, so the existence and uniqueness is really closely related to the existence and uniqueness in the discrete uniformization problem for simply connected surface. So, I'm going to be quick here. You have a triangulated PL surface, and so suppose I have a triangulation, and then it's a Delaunay. So this is a Delaunay condition, means for every edge in your triangulation, you take an edge in your triangulation, there will be two triangles adjacent to it, and there will be two angles facing it. So the Delaunay means alpha plus beta is the most pi, which we know from elementary geometry. It says that let's flatten this quadrilateral to the Euclidean plane. It says that if you look at the circle of one triangle, then the fourth vertex lies outside of it. And this is exactly the convexity in hyperbolic space, which you will see. Okay, so this is an empty circle condition. Okay, so that's a quick recall. I also mentioned that this is a basic lemma from computational geometry. The proof is quite simple, but we will need it, and so I'm going to recall that as well. So the lemma says for any compact, I need a compactness, PL surface D is a flat cone metric on this closed surface with cone point containing V. Anyone admits a Delaunay triangulation. And the proof is just, it's extremely naive. If you have a edge which violates Delaunay, alpha plus beta, you flip it. You replace this edge, that edge, by the edge joining the other two the other two vertices, and then the sum of these two angles is going to be less than pi, because the sum of the four angles is 2 pi. But this triangulation, this Delaunay triangulation in general may not be unique. So the problem is so-called critical Delaunay. So here is a situation. If you have an edge where the sum of the two angles facing it is equal to pi, alpha plus beta equal to pi, and this is sometimes called the critical Delaunay, and you can now do a flip. And if you do the flip, then this edge remains Delaunay, because the sum is again equal to pi. If this is a Delaunay triangulation, you do a flip, you produce a new triangulation, maybe I'm going to call F, and then you get a new flipped triangle F prime. It turns out this F prime is again Delaunay. And the proof is extremely simple, and the reason is we need to check this angle condition. This edge is okay. What about this edge, right? Is the sum of the two angles facing that edge still remain almost pi after you do the flip? The answer is yes, because this angle here is the same as that angle. These two angles are in the same circle, right? They face the same arc. So if we have a critical Delaunay, you can do the flip, and that will produce another Delaunay. And it turns out this is the only way to do it. So so the second fact which we will need is that any two triangulation F prime of the same surface are related by a sequence of flips through Delaunay triangulations. And the proof is quite simple, as well known. The flip, the only case you are allowed to flip is in the critical case, because you maintain both sum of these angles at most pi in that total triangle. So this is a fact which we will use. Okay, so here is the answer in some sense to, again, I should say nowadays there are many work on trying to define the discrete conformality. There are many generalizations of this, but circle packing and this is the most studied case, I can say. Let me use this side first. That's what is a little bit weak. So the answer in the vertex scaling case is that discrete conformal, which I'm going to tell you, discrete conformal for a polyhedral surface involves two conditions. The first is the Delaunay, and then the second is the vertex scaling. So we have to enforce these two conditions, and then this is one way of defining it. It looks a little bit complicated, but it turns out a result I'm going to tell you will justify this. Looks like a good definition. So to do that, we really need to ask the question: what is exactly the polyhedral surface that you want, that I want to study? What are the polyhedral surfaces? If I give you, of course, because every compact surface can be Delaunay triangulated, that's not the issue. The issue that I'm really interested in is infinite, because I want to have a discrete uniformization for any surfaces, compact, non-compact. In particular, I need a simply connected one. we have a simply connected, and then we have uniqueness that takes care of all surfaces. So, I give you a picture like this, just like a cone. This is a complex plane with one point, the cone point, and the flat metric. Do we really want to call this a polyhedral surface? And at this moment, I'm going to say no. I don't know how to define the discrete conformal class of surfaces like this. So I like to say, really, I want to enforce that Delaunay condition. So what do we mean by this? One means that we allow edge flips to critical Delaunay edges. And 2 is the vertex scaling. Okay, so that's exactly this picture. If we have a Delaunay triangulation and you have an edge, which is a critical Delaunay, allow you to do that. And the advantage of doing this is that we are not making any change on the underlying metric. It's just the triangulation that's changed. So this is a change of triangulation. So that's okay. No change in metric. And the second is allow a vertex scaling, but everything has to be stay in Delaunay. If SVTL is a Delaunay triangulated surface, and I make a change of vertex scaling, and the new one, I have to enforce it to be Delaunay again. So you can always do some vertex scaling, maintaining triangular inequality, or the Delaunay condition may be violated. If you do that, that's not allowed in this game. And so here is the definition that we propose. Do myself. In 2016. So two EL surfaces SVD1 and SVD2 are discrete conformal if the following conditions are satisfied. First of all, I should be able to produce a Delaunay triangulations of both. And that's not a problem if the surface is compact. If you view me a surface like that, this definition does not apply. So if there exists a Delaunay triangulation, EI of SVDI are equal to 1 and 2, and so that such that these two triangulations are related by these two steps, a sequence of these two steps. D1 and SVD2 are related by a sequence of these two operations. So that looks a little bit complicated. And to illustrate this idea, so suppose I give you a tetrahedron, the boundary of a tetrahedron. And we want to make a discrete conformal change of it. So what's the procedure? First, I need to check whether this triangulation that we see is Delaunay. If it is not, apply this flip operation to make it Delaunay. So we have to start with the Delaunay triangulation And then you are allowed to take a vertex V and put a scaling factor here, and then you can scale it. And so this is now, we perform a vertex scaling and make all edges through that vertex scaled by the factor. So, but you're not allowed to do it too much. If you, this has to be Delaunay triangulation again. So at certain stage of this stretching, you may run into a situation, for instance, these two angles appears to be critical Delaunay, alpha plus beta equal to pi. Then you are allowed to do a flip, which does not change the metric, but it does change the triangulation. And then keep going. Okay, so that's the discrete conformal. So the theorem that we proved at the moment is the following, which we call it a discrete version of a uniformization theorem. This is only for the closed case. For any closed PL surface SVD, any closed surface is discrete conformal. So I'm going to call this discrete conformal here, abbreviate as a DC, to a new PL surface SVD prime, unique up to scaling, such that this D prime has constant curvature. And the constant curvature is guided by the Gauss finite. So that's what we can prove at the moment. We call this a discrete version of the uniformization theorem. In fact, we prove a little bit more general. So we can prescribe discrete curvatures. So as long as you give me a discrete curvature satisfying the Gauss finite, and the obvious condition that the discrete curvature is always less than 2 pi at every vertex, there is a unique new metric, discrete conformal to the given one, with this given as a curvature. I definitely need to make a remark here. This theorem for the torus case was first proved by Filastri in 2008, but it's really not in this language. He was really studying the Bayer problems, the convex embedding of tori in cusp-3 manifold, and that translates exactly into this question. So there is really a convex geometry behind it, which I'm going to tell you. And also, Roman Krasnov is here, also recently gave a new proof of this using hyperbolic geometry. Okay, so this is not, I'm not going to talk about the proof of it, but I really want to see what happened to the non-compact case. Really, what happened if your surface is any connected surface, polyhedral surface, whether we can say something about this discrete conformal geometry. And for that, I need to tell you this wonderful viewpoint of this is a hyperbolic geometric viewpoint of Wobenko, Incal, and Springborn. I'm going to abbreviate VPS. I mentioned yesterday that they already noticed that vertex scaling it does not change the length cross ratio. And the length cross ratio, as you will see, should really be interpreted as the so-called shear coordinate in hyperbolic geometries. And so, so we're going to talk about the hyperbolic three-dimensional space as a complex plane plus the I'm going to take the upper half space model of the hyperbolic space, three-dimensional space. So the complex plane, these are the space where we use Euclidean triangle to build up polyhedral surfaces. And hyperbolic three-dimensional space, one model is the hyperbolic upper half space model. And the geodesics are either vertical lines or semicircles perpendicular to the complex plane. And totally geodesic surfaces are either a hemisphere perpendicular to the complex plane or a vertical plane. So I'm pretty sure you all know it in just to mention. And because of this, these are the totally geodesic planes, which are nothing but a circle in a complex plane, and that is this relation between the Delaunay, the empty circle condition, and the convexity in hyperbolic space, which I will show you in a minute. Okay. So let's now trace back a little bit. I give you a polyhedral surface, Euclidean, say, like this. The way to think about it is, of course, we cut the surface open and we get a collection of Euclidean triangles in the complex plane. So I have, this is my triangle tau, and I have a Euclidean triangle tau in the complex plane, and I have another triangle delta, and I can put it delta somewhere, right? And these triangles are glued together along their edges by some isometry. There is isometry. F is an isometry of the Euclidean plane, doing these corresponding edges, and that's the way to reconstruct the polyhedral surface. Now this amazing idea from BPS is this. Every Euclidean triangle is a convex hull 3 points, V1, V2, V3. Okay, the vertices of it. Now you can take the convex hull of these 3 points in hyperbolic space. Convex hull in hyperbolic three-dimensional space of V1, V2, V3. And this is sometimes called ideal triangle. So the shape will be something like 2 points will give you a geodesic, and tau star. So that's a hyperbolic triangle with vertices at infinity with the same vertex. And so you have also a picture here. Okay. And now here is the interpretation of the length cross ratio. So the picture is, suppose you have a quadrilateral, tau and delta. These are two triangles glued together. And over that, and you have this ideal union of two ideal triangles. I don't draw it nicely. Okay. So these two ideal triangles, you can develop it, and that becomes an ideal quadrilateral in hyperbolic two-dimensional plane. Okay, this is tau star and delta star. And so the question is, what is the meaning of this length cross ratio A and A prime, B and B prime? A prime, B prime is equal to the exponential of the distance. This distance is called the shear coordinate. And so what is the distance? For this delta star, you have an inscribed hyperbolic circle, and you have another inscribed hyperbolic circle. And so the distance here, this D, is called the shear coordinate of this hyperbolic ideal tetrahedron, and this is exactly that. And the computation is really simple, but the observation is quite tricky. So now you can rebuild, for any polyhedral surface, you can build up a hyperbolic surface associated with it. And so what's the idea? I take these two Euclidean triangles, tau and delta, glue them together along an edge, along this edge where you produce here, right? By a Euclidean isometry, but every Euclidean isometry is an hyperbolic isometry. Euclidean isometries are translations, and that extends to a translation of the upper half space, which is isometry, and so is a Euclidean rotation, which extends to a naturally and hyperbolic isometry in 3D. And so you use this Euclidean isometry to glue Euclidean triangles to produce this. Now you may as well to use their extension, FR, glue along their similar corresponding edges. And so this is the edge over the Euclidean triangle. This is the edge over that. So using these gluing, and this gluing is exactly saying we're doing this process. Okay. So the answer now is given the PL surface SDD, by taking this hyperbolic point of view, I produce a hyperbolic metric. But it depends on the triangulation. So this is a hyperbolic metric. It's a complete hyperbolic metric on this puncture surface, because these punctures correspond to the ideal point, which appears in infinity with cusp end at all vertices. And what they observed is this. If you do, this should be triangulated, sorry. So I'm going to put a D here. And from all of these points of view, you see that if you do a vertex scaling, it does not change the length cross ratio. It does not change the way that they glue together. So they observe this really beautiful result that if, maybe I'm just going to say the invariant under. So for every polyhedral metric Euclidean, you can produce a complete hyperbolic metric on the puncture surface, and that assignment is invariant under vertex scaling. So that's really a very beautiful point of view of looking at the vertex scaling. But unfortunately, which I also missed, that this metric changes if you do a flip. So so I'm just going to see this. Okay. So you take your triangulation, take an edge in it, and you flip it. Then the resulting hyperbolic metric is not isometric. And that somehow is the issue. The Delaunay is the main issue that I missed for 10 years. And so vertex scaling we introduced in 2002. And we figured out in 2013. And BPS also missed the Delaunay condition. So if you enforce Delaunay condition, these two are the same. The second remark is if F to F prime is a flip to Delaunay triangulation, then dF is isometric. And you can see it easily, and that's where all of these Delaunay conditions appears. So, so here is a picture of the Delaunay condition, and so let's see what happens when you do a flip in 3D point of view. So here I'm going to draw the picture here. I have a Euclidean triangle. These two Euclidean triangles they are cyclic, lies in a circle. And we now perform this BPS construction. You produce ideal triangle over this and over that, but they all lies in the upper hemisphere with the boundary, the second circle perpendicular to it. And so what happened is both these triangles lies in the same two spheres. So what happened is now, well, what happened is we are doing this operation on the top two-dimensional spheres. If it's a Delaunay, this operation does not change the metric at all. Okay, so that's this B. I definitely admire this hyperbolic point of view, and here is really the better definition of discrete conformal. And this is the one that we're going to stick to it, and we can propose really what is a discrete uniformization problem. So two polyhedral surfaces. Or maybe let me phrase this one. Yeah. Before I do it, it's now clear that what is really the classes of surface that we want to study to produce this notion of discrete conformality. And so here is our new definition. This is my convention. If you give me a surface outside of this category, we don't know how to define discrete conformal change. So a polyhedral surface from now on is a connected surface with a discrete subset of it, and D is a flat cone metric. It's the same thing, such that it admits a Delaunay triangulation. Okay, so all the polyhedral surface I'm going to talk about from now on satisfy this condition. If your surface is closed, no problem. That's guaranteed by the computational geometry. But it turns out there are triangulated surface, polyhedral surface is infinite, but you cannot make a Delaunay triangulation out of it. So it's a very subtle situation, but let's stick to that. So these are the polyhedral surfaces I'm going to talk about. And then two polyhedral surface SVD and SVD tilde are discrete conformal, if and only if you go to BPS setup. S minus B. I'm going to write 1 and 2 to avoid too many indices. So we now observe that if you stick to Delaunay triangulation, you can now just remove this E being Delaunay, right? Just pick one Delaunay triangulation, and this BPS construction is canonical. So there are no ambiguities. So this is coming from BPS construction. So these two metrics, B2 star, are isometric. I need to add one more condition. This is really coming from Teichner theory. If you only assume isometric, that's not enough, because of the topology here, I and isometry, I, which is a homotopic with identity. Okay, so that's our definition. This works for all surfaces now. And let me give you one example, which shows where this Delaunay condition comes in. So these are sort of the canonical examples which will appear in the discrete uniformization conjecture we're going to propose. So let's take a polyhedral surface, which is a complex plane, a discrete subset of it, take the standard metric. Okay, so this is just a flat metric. I take a discrete subset set of it and consider that as vertices. And now the question is, what is this BPS metric? So the standard metric, what is this? And this is where the convex geometry Samvara problem, Cauchy problem comes in. And the answer is, this is exactly the boundary of the convex hull. The boundary of the convex hull of V in hyperbolic three-dimensional space. It's isometric. So let me just draw a picture. By our convention, this set has a Delaunay triangulation, right? All polyhedral surface I'm going to talk about. So there is a Delaunay triangulation coming out of it with vertices given by V. So you take a triangle, and then by BPS, we have a convex hull, this point comes in. So there is a 4 star, which is ideal hyperbolic triangle, tap over it, and that's a piece of a two-dimensional object. And what is this? Well, that's exactly a face. All star is a codimension 1 face of the convex hull because of the empty circle condition. If you draw the circle here, if you draw the circle through a 3 point, there is this hemisphere over it, right? 3 points. And this hemisphere contains no point in V by empty circle conditions. And so this says exactly this is a supporting plane for the convex hull. And this triangle lies in the supporting plane, so it's a codimension 1 faces. And that's exactly how we construct all of these guys, right? So you put a cap over it because of the Delaunay, and that's equal to it. So this is now the final picture. So let me now formulate what is the discrete uniformization problem for all polyhedral surfaces. And I would also like to tell you some progress is being made. So here is our conjecture. This is really, we try to mimic, this is by Feng, myself and Wu. Just like in the classical uniformization theorem, you only need to address the simply connected one, okay? So we're gonna address that in the simply connected case. And so, let's let S be a non-compact, simply connected surface. If it's compact, the previous theorem basically takes care of it. Then the conjecture says that for any PL surface S, B, D, The PR surface now we have to enforce this condition. So this is a piece, is a convex, this is a flat cone metric on the surface, this vertex right here. But it admits a Delaunay triangulation. Otherwise, N1 is discrete conformal to unique optimal transformation. To the following. So to the standard complex plane, it's a discrete set picked like this. This is the standard picture for discrete and the standard Euclidean metric. Or the unit disk, you pick up a discrete set in D standard. The D prime are discrete. Okay, so that's a discrete uniformization conjecture that every polyhedral surface simply connected always looks like what we can imagine some discrete set in C simply connected, or the complex plane is a discrete subset here. Yeah. Okay, so what do we know? But I also like to phrase this in terms of the wire problem. So, this is conjecture 1, conjecture 2. It's a little bit weaker, but it's more closely related to the classical wire problem. You see, when I give you this object, according to BPS, it's really I give you a hyperbolic metric. Still assuming it's simply connected. So it's a simply connected surface with D removed, and D is a hyperbolic. Maybe I'm going to put D stuff. It's a hyperbolic, complete viscous band. So these are exactly the metric coming from BPS construction. And what does this conjecture says is that everyone is, it is isometric to the boundary of convex hull. The boundary of the convex hull of a discrete set C lies in C, or boundary of convex hull of a discrete set in the interior open disk. And so for that, I need to rule out the boundary, and so usually it's written as a U union D complement for a discrete in C or D and unique opticometry. Three-dimensional space. So this is clearly a wire-type problem. So I give you a metric on this puncture surface. The curvature condition is given. By the way, it's known that the boundary of the convex hull is always a complete hyperbolic surface. And so this is a question of the other way around. If your set is a finite, this is sort of the Cauchy type rigidity. This is the one for infinite number of Oh, that. It's really, you take two ideal hyperbolic triangles and glue them together. So let me tell you one consequence of conjecture 1 that may be interesting to see it. This is the corollary. Let's just recall the classical uniformization theorem. What does it say? Here I have any connected surface with a Riemannian metric. Give you any surface. And then within its conformal class, it's either classically conformal to the two-sphere, the standard metric, or then we have the complex plane, the standard metric. Maybe I'm going to just draw a picture. Then the complex plane, Then, or to a cylinder, S1 cross R, it's a flat, or to a torus, S1 cross S1, and then the rest of it is hyperbolic. So it could be compact and non-compact. And in this class, it's unique. In the hyperbolic case, it's unique. In this case, it's unique up to scaling. In this case, it's not unique, but it's unique up to Möbius transformation. And so suppose one can prove this. What does it say for all polyhedral surfaces? So here you have all polyhedral surfaces is going to be discrete conformal to, how does it look like? It's exactly the same picture. Either a two-sphere with finite set of points, or it's infinity here, C, or just put the infinite number of points on the cylinder. It's a Delaunay triangulation, or a torus is a finite set of points, and the rest of it are all, you take a complete hyperbolic metric on your surface and a discrete subset of it, which is supporting a Delaunay triangulation. We still have the uniqueness, we still have the scaling, and Möbius transformation. So that's the complete picture of all polyhedral surfaces if this conjecture is true. Okay, so I have a few minutes left, and so let me tell you what progress we've been making. So this is a recent work with Wu. We can show conjecture to the existing positive. So existence of conjecture to both. And so in some sense, it says this. And we are almost sure we can prove this in the uniqueness here. But the main problem is really the Euclidean plane case. And so let me, before I show you the slides, let me finish the Blackboard talk by asking this really simple question, which has been puzzling me for a while. I think it's quite interesting. So a major problem is this. If I give you two discrete sets, V1, V2, discrete subset of the complex plane, such that if you take the boundary of the convex hull of them in hyperbolic three-dimensional space, it's isometric. And so this is really a Cauchy type problem. So the boundary of the convex hull are isometric, and then the conjecture is that V1 and V2 differ by Möbius transformation. So that's the rigidity problem which we run into. Okay, so let me now show you a couple of pictures, and I also like to tell you how we prove this quickly by following the circle packing case. And so there is a wonderful proof by her using Schwartz lemma. And so I'd like to show you that, the discrete Schwartz lemma. So this is a couple of pictures I promised at the beginning. So this is a Doyle spiral picture. You take a standard lattice and do that, and the conjecture is this is the only one. It turns out there is a similar conjecture we discovered. So for the circle packing, the length is given by sum of the two radii. In the vertex scaling, instead of doing, we follow exactly what Doyle did. Instead of sum, just multiply. So you assign these lattice point a number, you multiply them together, assuming they satisfy triangular inequality. And if this map is a group homomorphism, the metric is flat. It's a spiral. So we conjecture this is the only case. And this is an example of a circle packing of the unit disk. It's infinite. So this is the one I'm going to tell you the uniqueness. And this is a picture of Vaden-Solomon's proof of the substance conjecture. I just want to show you that this is how we see Riemann mapping acts. This is a normalization condition sends the center to center. So this center here is sent to that center, and this point is sent to that point. And you see the curvature effect here. So that's this is a famous picture by Ken Stephenson. And this is the algorithm we produced to map a uniformization theorem in action. And so this is a 3D scanned human face. Okay, so that's a 3D scanned human face interconnected. Uniformization says we can map that to the unit disk, preserving angle everywhere, and that's coming out of this vertex scaling operation. So we see that. And this is the pictorial illustration of the KAT theorem. I have a simplicial triangulation of a disk. I can produce a circle packing of the unit disk where this is color coded. So this vertex corresponds, pink one corresponds to this pink circle tangent to the boundary. Okay, so that's the illustration. And so let me quickly now, have 2 minutes left, tell you first proof of the uniqueness. It's absolutely textbook proof. So the theorem says, suppose I have 2 circle packing of the unit disk, it's the infinite circle packing. They are isomorphic. So you have another pattern like that. There is a 1-1 correspondence between these circles and tangency. If that happens, these 2 patterns differ by a Möbius transformation. So it's really about hyperbolic geometry. Hyperbolic geometry is invariant under Möbius transformation. Basically, you have another picture like that. You take your first circle here and the first circle the other side. The theorem says that the hyperbolic radius of them are the same. And the proof is, again, if we recall the proof of the classical uniformization theorem, it's a Schwarz lemma. And so this is the Schwarz lemma we're all familiar. F is a holomorphic map from a disk to a disk, then it decreases hyperbolic distance. And so D is the hyperbolic distance. And the analog of that was proved by Bearden and Stephenson in 1990s, and it's a finite setting. So suppose D bar T is a triangulated compacted disk. This is a finite triangulation, and we have 2 circle packing. But now we have to use hyperbolic geometry. So all triangles, hyperbolic triangles. Okay. This is KAT coming out of this triangulation, where the boundary circles are all tangent to the unit circle. And so these are horocycles, and the radii are all infinity. And the right-hand side is any triangulation, any circle packing inside the hyperbolic space. And so think of that as a discrete map, discrete holomorphic map from one to the other one. And their theorem says that the KAT radii is always bigger than or equal to the radii of any other one, so the corresponding radius. And so the KAT is the hyperbolic maximum. This is a discrete uniform, discrete Schwarz lemma. It's very beautiful, and the proof is also quite simple. So now let's prove her theorem. So this is the discrete Schwarz lemma that I just showed you. And first observation is extremely simple and elegant. And he says that now these are all hyperbolic circles. Let's allow these boundary circles to be a little bit larger. I allow them to cross the sphere to infinity. So these are no longer circles in hyperbolic space, but curve of constant curvature. If you do that, the angle, the radii is even bigger. So the radii of this is bigger than equal to the radii of the KAT, and is bigger than that. So this is a slight extension of it. Now here comes this proof. So suppose we have 2 infinite circle packing of the unit disk. We have the same nerves, and I label 1, 2, 3 in one circle packing, and in the other one like that. So there is 1-1 correspondence between these circle packings, and we want to show these 2. They all have the same hyperbolic radii. The picture is like this. You take a scalar lambda slightly bigger than 1, okay, and multiply this p by lambda, and you get this picture. So this red circle is now the multiplication P by lambda. If you do that, there's only finite number of circles intersecting the unit circle. These are going to be the yellow circles. It's only finite number of them because the picture is locally finite. Now you look at the corresponding circles in P prime, and that's exactly this picture. And so if you multiply the radii of P by small lambda, arbitrary small, it's going to be bigger than equal to the P prime. And that lambda goes to 0 on that equal. So that's the proof. Okay, sorry I take a little bit longer time. Thank you for your attention.